Alright, we're going to do parallel forces part 2. Hopefully you've watched part 1 so you have an idea about parallel forces. And we're going to do a particular problem here. We're going to say we have a scaffolding. So a big scaffolding here. And we're going to it's going to be supported on both ends by some kind of support. So I could make these like chains up on top, or I can say that they're just support, some kind of supports here. And we'll call this one here F1, and we'll call this one F2. And the problem is we don't know what either of these forces are. So we're going to have two unknowns, which sometimes makes things very scary. So let's say that this scaffolding is divided up into three parts, a meter each or something. I don't know, something like that. And so we're going to have there's going to be a guy that's standing on here. And let's see, this guy here is going to be standing on the 1 meter mark. It's a bricklayer. So here he is. He's standing on here. And let's say he weighs like 800 newtons. So we're going to draw a vector down here that represents 800 newtons. That's how much he weighs. The weight of this scaffolding it's a uniform scaffolding, which means the weight needs to go in the center of gravity, which means the center of gravity would be in the middle of the object. And the weight of this scaffolding is 750 newtons, we'll say. 750 newtons. And we'll say there's a pile of bricks on here, too. And we'll say it's right in the middle also. And the pile of bricks weighs 320 newtons. So I could actually add on more weight there, 320. And I could go ahead and actually sum these together. That would be 1070 newtons here in the middle. Okay, so what I want to do here in this problem is I want to figure out what is the force on F1 and what is the force on F2. Now, the first thing, remember, there's three rules. And the first rule is ups have to equal downs. So we're going to make a chart here first. Ups equal downs. Or we're going to make a chart anyway. And my ups, I have an F1 and I have an F2. And my downs are 800 plus 1070. So my total downs are 1870. And my total ups are F1 plus F2. And we know that these have to be equal if we want this whole thing to be in equilibrium, because that's what we're trying to do. Now, I think it's common sense that these F1 and F2, they're not going to be equal themselves. They would be equal if this guy happened to jump up on top of these bricks. Then all the weight, the bricks and the scaffolding and the guy would all be in the center, and so it would be evenly distributed amongst F1 and F2. We could just take half of 1870 and know what F1 and F2 are. The problem is that they're not all in the center. The guy is closer to F1. So you can imagine that the most of this 1870 will be supported by F1. And F1 will definitely be greater than F2. So we're going to start here with our ups equal downs. That's going to be important information, which we'll use in a little bit. But now what we want to do is we want to figure out what are F1 and F2. So I need to do torques now. I want to do clockwise and counterclockwise torques, because I know they need to be equal. So where am I going to use as my reference point? Well, this is where it gets to be important to know where you should use, because I don't really want to use one of these 3 points, because no matter what, if I do that, I'm going to have two unknowns still. If you remember in the part 1, if I can choose a place where I already have a force, and that means I don't have to worry about that force. Well, that's going to be really, really great if I'm going to, if I have the force I don't know. If I don't know a force, then I'm going to go ahead and choose as my reference point F1. That way I don't have to actually even have to worry about F1 when I'm figuring out my torques. So I can measure some torques here. I can say 1 times 800. That would be a, what kind of torque would that be? That would be, it's going to go around this way. So that would be a clockwise torque, 800. And then I have 1070 times 1.5. 1070 times 1.5 meters or feet or whatever. And that's also going to be a clockwise torque, and that is 1605. And then what do I have for counterclockwise? Well, I have one force here. It's called F2, and it's 3 meters away. That would be a counterclockwise torque. So I'm going to write 3 times F2. I don't know what F2 is. So if I total these up here, I'm going to have 2405 worth of clockwise torque, and I know that would have to equal my counterclockwise torque, 3 times F2. So to figure out F2, all I have to do is take 2405 and divide it by 3. And I'm going to be able to get my F2 force, and if I do that, you'll see that this force here is 802 newtons. Okay, now what I've seen some students do is they said, okay, now let's figure out F1. So we're going to come over here and use this as our reference point and do the same thing. And you can totally do that if you want. You could take 1.5 times 1070 plus 800 times 1.2, and that should equal F1 times 3. But the easiest way to do that is we already have our ups and downs. We know F1 plus F2 equals 1870, and we know what F2 is. So to figure out F1, all I should have to do is take 1870 minus 802 to get my F1. And then you'll see your F1 is about 1068 and newtons. And so that makes sense because the man is closer to F1, so this F1 needs to be bigger than what the force supporting the other end is at F2. So it's important when you have two unknowns in your problem that you're probably going to take one of those unknowns and use that as your frame of reference to calculate your torques from, because you don't need to actually use that force. So you take a 2 unknown and you reduce it to a 1 unknown, which is very helpful. So that was part 2 problem for parallel forces. Hope that made sense.